I can hand over to Mark.
Great.
Oh, but I should also say the last thing I forgot to say was he's also the author of one of what I consider one of the best introductory machine learning textbooks. We actually use it in our introductory machine learning course at Chalmers. So
very good. So I flew over here yesterday all ready to talk about stochastic modeling of urban structure, and then got an email about 9 o'clock yesterday evening from DevDat asking me to talk about something else, which I am hopefully about to do. So there are no equations in this here. And the question that I want to pose is data science hype or hope? And in particular, what I'm going to do is I'm going to frame data science within the engineering professions. And there's a phrase that's emerging called Data-Centric Engineering. And so the question is this just a whole load of hoax, or is it the dawn of something completely new as far as the engineering professions are concerned? Now, you heard about the Alan Turing Institute. Now, this is an institute that was set up by the UK government in an attempt to establish a data science capability within the UK at a national level. So we were originally set up as the UK's National Institute for Data Science. And just recently, a government report on artificial intelligence also recommended that the remit of the Alan Turing Institute be now extended to data science and AI. So the Alan Turing Institute is the UK's National Institute for Data Science and AI. It started off with a competition, like most of these things, to establish the institute. And that competition ended with the selection of 5 universities from the UK: Oxford, Cambridge, University College London, the University of Edinburgh, and the University of Warwick. And 2 years ago, they established the institute. And since then, a number of other universities have now joined to form the institute and to extend it. So the initial period was based around London. So academics from each of these universities were seconded to the British Library, where the hub of the Alan Turing Institute is based. And now a hub and spoke model is being developed across the UK. And now that the hub is working reasonably well, we are now looking at developing the spokes to other centres of excellence within the UK. So, of course, the legacy of Alan Turing, everyone certainly knows. And in particular, you know, his work in theoretical and applied mathematics, in engineering and computing, and even in biology, right? And, you know, we consider that these are the key disciplines: applied mathematics, mathematical modeling, engineering, computer science, are really the key disciplines that form the basis for the field of endeavour that is called data science. And likewise within artificial intelligence, it was Turing who posed the question, can machines think, in his 1950 paper, Computing Machinery and Intelligence. So this is really the intellectual DNA that the Institute in London, the UK Institute, which is currently based in London, takes its pedigree from. The goals of the Institute are fourfold. The first one is that it has to develop world-class, world-leading research in data science. But not only that, it has to be able to translate and apply that research to real-world problems. So, to support the creation of new products, new services, new processes, new jobs. So this is a very important goal of the Institute. And of course, if we are going to be doing world-class research in data science, and if we're going to be helping support the innovation of data science and artificial intelligence, then the Institute is going to have to take on the responsibility of training the next generation of data science leaders. And finally, we spend a lot of time working with government and government departments and shaping policy in various guises. I, for example, am on the Defence Security Executive of the Ministry of Defence, advising on how applied mathematics, statistics, computer science, data science can help with defence and so forth. So that's the Alan Turing Institute. I should say that we have round about 200 researchers at the doctoral student level, at the postdoctoral level, at the research fellow level, and then at the associate assistant and full professor levels, all based at the British Library. So it's quite a busy place. Round about the same time that the government was making a case to establish an institute for data science, the Lloyd's Register Foundation commissioned a foresight review on what the impact of big data would be on commercial enterprise, and in particular in engineering. And one of the recommendations of that foresight review was that a program of research would be established in collaboration with the Alan Turing Institute on what they called Data-Centric Engineering. And this is a large, substantial program of work. And I was appointed as a director of that just under a year ago. Data-centric engineering. Some of you are saying, I've heard it all before. This is just another little point on the Gartner hype curve that's going to go up to the top and then go all the way back down. This is just hype. And indeed, for those of you who recognize who this is Lord Kelvin. It's a beautiful painting that sits in Bute Hall at the University of Glasgow, my former university. And what Lord Kelvin is ascribed as saying is that if you can measure something, you can improve it. If you can measure something, you can know it. And in many ways, engineering has always been data-centric. Engineering has always been about making observations, making measurements, collecting data, analyzing that data, and acting upon it. So one could be forgiven for saying data-centric engineering, another load of old hype. Well, let me try and make a case that, in fact, this is not hype, but in fact, a very exciting time to be in the engineering professions across all sectors. When I established the program on data-centric engineering at the Alan Turing Institute, I gave it 3 grand challenges, which were going to be the concentration points for everything that we did in the program. And the 3 grand challenges were: 1, we wanted to be able to enhance the resilience and robustness of critical infrastructure. Now, critical infrastructure could be transport infrastructure in a city. It could be the processing of liquid natural gas in some refinery somewhere. So infrastructure that is critical for human and economic enterprise. And we heard this morning why security, why privacy is so important. And in a data-centric age where critical infrastructure is being instrumented with sensors, with networks of sensors, and is gathering data and intelligence at an enormous rate, the threats posed upon it to cyber attack and so forth increased dramatically. And so one of the main goals of this program, or challenges, is to ensure that we can make more resilient our critical infrastructure. Now, if we're going to do that, the next challenge is going to be, how do we monitor complex engineering systems? And these are engineering systems which may well be socio-technical systems, not just technical systems. How do we monitor them for rare events that have got high consequences? Most engineering systems experience rare events on a very regular basis, and those rare events actually come to nothing and are not terribly important. But we're really interested in those black swan events, if you will, that really do have high consequences. And then the final one is the whole notion of design, and the fact that, I mean, what's amazing now is that we can actually scan whole buildings and then, take the scan of that building and make it into and then import it into some CAD facility to devise a digital twin. And all of the small micro-scale characteristics can be captured. And we can do that at a building level, at a component level, and even at an urban level as well. So those were the three grand challenges. And similar to the actual Alan Turing Institute, the program, it has four main focuses of activity: research, providing intellectual leadership, translating that intellectual leadership into industry innovation. And this is probably one of the most challenging components of the work that we're doing. And I'll talk a little bit about that shortly. And likewise, if data-centric engineering isn't just a bandwagon that's going to be forgotten about in 5 years' time, and we do need to train a new class of engineer, then we better start thinking about the engineering curriculum. And so we're doing an awful lot of work on training of engineers in data-centric capability. And the first exercise is actually building a program of doctoral training in data-centric engineering. And then the final one is standards. Something that we, probably academics, tend to forget is that products, services, don't come into being just like that. There has to be standards. Standards have to be devised. They have to be maintained and kept and updated. And so, again, in a data-centric engineering environment, then we need to start looking at what are the standards for data, what are the standards for the quality of data, for the governance of data, and so forth. This is the program. So I lead it. I have a program manager that looks after all the day-to-day things. And I have a strategic leadership. There are 3 senior academics who all hold chairs, professorial chairs. And each of those leads one of the 3 grand challenges that I described to you. And then we also have someone looking after the education component, and someone who is a topologist, who actually is looking at how we can do blue sky foundational mathematical or applied mathematical research that is aligned with what potential technologies would be required from each of those 3 grand challenges. And then I have a number of group leaders who are all career young academics, either at the assistant professor level, and they're charged with the responsibility of leading a group, bringing in funding, defining projects, and delivering on those projects. And we've got quite a number of projects going on at the moment. All of them are aligned with various engineering companies and commercial concerns, and you can see a couple here. I'm going to give you an example of that translation. And I'm going to give you an example from my own experience. You've all probably heard, or vaguely heard, of a company called NCR. NCR was the precursor to the great IBM. So this is a company that's well over a century old. NCR is an acronym for National Cash Registers. And guess what they started business doing? Building and selling cash registers. Now, of course, they're probably far better known for producing automatic teller machines and other financial services and so forth. Big multinational company. They approached my research group because they had been given a particular challenge. And the challenge came from their mainly Far Eastern banking customers who wanted a means of being able to assess the validity of banknotes that were deposited into the ATMs. Okay? So typically what would happen is that banknotes that are deposited into the machines would be gathered and then sent to the bank and manually or semi-automatically checked for validity. You know, is it genuine? Is it counterfeit? Has it been through a washing machine and a tumble dryer too many times for it to be set back into into distribution? But what these banks were wanting was the ability to actually recycle the notes. So as soon as a banknote or a number of banknotes were deposited into the ATM, they would be made available immediately for withdrawal. And so what that then meant was that it was incumbent locally at the machine to do the security checking. And now, what's interesting is that the sort of or the manual checking of banknotes by the use of security features that are engineered into the notes actually don't make much sense or use when it comes to automated counterfeit validation or detection. And the reason for this is, well, it will become apparent just in a moment. So this was a challenge. We wanted to verify and validate banknotes. Very difficult problem, one, because you had to be able to support an enormous diversity of banknotes and currency. And the geographic variability of the quality of notes was very high, depending on whether you were in an environment that perhaps the weather was humid or dry and so forth. And of course, the key thing is that really what you're trying to do is validate banknotes, in other words, discriminate them from counterfeits. And one of the things that is very limited is any intelligence or understanding of what characterizes a counterfeit. And as soon as a counterfeit is identified, then the legal forces get brought into play and the counterfeiting ring is shut down. So this was not a standard sort of machine learning problem of classification, where we would have a number of samples of genuine and a number of samples of counterfeit notes. The key is that all we could have were genuine notes, because the counterfeit notes really didn't make much sense, because we would never see counterfeit notes like the ones that had been captured again. So what was the approach that we came up with? Well, I'm a statistician, so we said, well, let's just look at this as a sequential hypothesis test. Is the banknote in front of me genuine or counterfeit? And we test against the hypothesis that it's genuine. And what this allowed us to do was mean that we could have a template for every possible type of currency and every possible type of banknote associated with that currency, which was unique to the local machine and would adapt, right, at that particular machine. So what did we do? We looked at the color of money. Now, I'm not going to give you all the details. We didn't use deep learning. We actually used the tools that were required for the job. And that meant that we used really high-tech mathematical statistics from the 1930s. That's all we needed. Well, actually, that's not strictly true, because we also had to use some mathematics from the 1980s, some optimization theory. But pretty much, it was a fairly low-tech solution in comparison to some other things that we would see. The postdoc in my team that actually did the work was hired by National Cash Registers to develop the technology. The technology was taken from basically what was described in this paper. And over a number of years, it was developed into a service which is now possible to be shipped with certain NCR products. And this is the outcome of it here. And there is one bank in the UK that actually uses it. And this was a great example, because really all that we used was data and some schoolboy statistics. Okay, it wasn't really schoolboy statistics, but it wasn't rocket science. But it did rely on lots and lots of data. And there we have the mapping from the paper to the actual product. So this was a great success for us. Here's another example which we're currently working on now, and in fact this time next week I will be in Amsterdam at a project meeting. This is part of our current program, and you've all heard of additive manufacturing, and there's a small company in Amsterdam who have developed the capability to 3D manufacture fairly large structures. And the one that they're currently working on is a bridge, a footbridge, a pedestrian bridge that will go over a walkway in Amsterdam, and it will be the world's very first 3D printed stainless steel bridge. Not sure how to get this to run again. Let's just try.
MX3D, based in the Netherlands, is planning to print a 3D bridge over a canal in the center of Amsterdam. Yes, that's a real canal
Could we
with
put the
real
sound
running
down?
water underneath. The inventors
Thank you.
setting metal structures in all
So one of the exciting things about this is that it's taking new technology and really expanding it into a completely new area. The thing is, we don't know what the structural properties of 3D printed steel is. Is it the same as rolled steel? There are no design standards for 3D printed steel. And so what our program is doing is working with structural engineers and applied mathematicians and statisticians and computer scientists and machine learning, and instrumenting the structure to gather as much data as we can about the bridge when it is deployed and when it's actually in use. So in essence, this will become a living laboratory, and we're really delighted that we're leading on this sort of technology. The other sorts of things that we're working on, I think I've only got 5 minutes, so is predictive maintenance. And also, this is a very nice example where we're taking very complex computational fluid dynamics and making it available as a tool for setting up. So this here is actually cleaning out pipes in a food processing plant. So making the power of computational fluid dynamics available to process operators to be able to optimally set up process plant. This was a tablet application that our software engineering team developed based on some new CFD codes that we developed. So what's the ongoing plans? Well, we are going to expand the program internationally. We've already started a relationship with Shell in Australia, and I would be hoping that perhaps some discussions today and tomorrow might also spark up some international expansion here in Sweden. So, let me conclude. Is this hype, or is it something more than that? Well, I would say that data-centric engineering is really forming a concentration point, a nexus, if you will, of the mathematical, statistical, computing and engineering sciences. It's transforming engineering practice, and it's having a huge impact on the engineering professions, and all of the professional engineering institutions have sat up and are taking note of this. As you heard me speaking at the before lunch, I'm not one for shouting about big data and artificial intelligence. I like to call it what it is. And so for me to actually say that this is not a fashion or a hype is actually quite a big deal. I also don't believe that we'll be talking about data-centric engineering in 5 years' time. I think we'll just be talking about engineering, because it will be embedded in everything that engineers and the engineering professions do. But we need to make that transformation, and we need to do it now. It is definitely being acknowledged as a disruptive force, and many large companies that are both non-digital born and ones that are digital born are looking at their business models and trying to develop them in this data-centric age. I think that we're making, well, we certainly have a lot of potential for impact. I mentioned this additive manufactured bridge, which is a really cool project. We are defining a new discipline, and in fact, Cambridge University Press are going to be setting up a new journal on data-centric engineering. So, the intellectual foundations are being laid for a new discipline, but also something that is going to impact on the engineering professions. And let me just say finally that at the Alan Turing Institute, one of the things that is incredibly exciting there is that it is fundamentally a multidisciplinary environment. I can speak to topologists, I can speak to applied mathematicians of every hue. I can speak to social scientists. I can speak to ethicists, statisticians, although not too many people come and speak to us, to be honest. Computer scientists, again, of every hue, from artificial intelligence, machine learning, to algorithms, to software engineering. And it's free from the sort of classical academic constraints that we all have. It's truly a fantastic environment to be in, and the ideal environment to be developing a program such as data-centric engineering. So I think I've spoken for 40 minutes, or just under, and I'm finished, so thank you.
Questions? One at the back there.
Hello. Hi. I'm a system scientist working with the development of businesses with IT. And when looking, for example, into additive manufacturing, do you see any chance of taking this thinking and put it into context when we organize operations in enterprises? Just add exactly what is needed to produce or pursue whatever operations, instead of the way that we all usually tend to say we need to set up a big organization structure, we need resources, and we add a lot of stuff that is not really directly needed for the precision of like in additive manufacturing techniques and strategies.
So I didn't quite, my
Do
hearing's not too
you
good.
think we could use the thinking behind additive manufacturing when thinking about the operations and organizational design? And actually just add what is exactly needed to pursue the operations, and not building so much structure that we tend to do in organizations.
I'm not entirely sure, to be honest with you. I think you should come and speak to me, because I can't quite make out what your question is.
I think he was trying to ask if you can take philosophy or the thinking with additive manufacturing and moving it into thinking about business structuring.
Oh, right. So, I mean, certainly, one of the strategic leaders actually is a systems engineer, and is very much taken and has been advocating a systems view to engineering design, but not only to engineering design, but to the socio-technical aspect of engineering. I think this is one of the things that we sometimes forget, that we may well have a technical solution, but that technical solution is really not much use within an organizational setting. And so, you know, this whole idea of taking a systems view where you know, we really are looking at an overall interacting system, which has a huge social and human aspect, is certainly one that's very important.
More questions?
Yes. So the question is the whole idea of data-centric engineering one that gives us improvements on existing engineering and engineering practice, or is it going to do something completely new? And I would say it's both. I think that there is clearly an absolute transformation. Now, I give you the example of the 3D printed bridge. That is transforming material science. It's transforming structural engineering. This is a completely new material. They don't understand it. There are no models for it. So this is a complete transformation. But there are other aspects where being able to measure just that little bit more, be a little bit more precise, can then improve, of course, what is existing. And one of the things that I certainly don't want to be is a revolutionary and throw everything out. I think what is good and what still works should remain and be improved, but there are always going to be disruptions and transformations that typically we never foresee. So I would say that this data-centric revolution, this data-centric era is going to see, you know, improvements which may be delta or epsilon improvements and completely new initiatives.
Okay, let's thank Mark, and let's hope that we will